is an irreducible representation of the locally compact group GA that occurs, and I have to write occurs quotation marks because it's nicely defined in composition. Regular representation R of GA on the Hilbert space L2 and what we are doing, it's understood here, we will bump this up a little bit later, but we're as concrete as I possibly can. But we're taking G to the GLN, taking base field to be the rational, the arbitrary field, and we talked about last time what the Adels were and why the GQ embeds a discrete subgroup of the Adels, and so this is a slight, it really not as big a generalization as it looks. It is something that's akin to what people have studied 50 years ago, 70 years ago, where they talked about a real group, a real Lie group, modulo a discrete subgroup. And if representations of a real Lie group are interesting enough, but when you divide out by a discrete subgroup, for example, the group of integral points in situations where that makes sense, then whatever was interesting about the individual irreducible representations of the real group gets really, really interesting when you ask. So I've got to say a little bit more about well, this, and specifically what goes into an automorphic. What are the things that are built into an automorphic that make it interesting? So I'm going to be stating this fact. Now this is not a hard fact, and the person that wrote it up for general consumption, like many of the articles, the basic articles of this are the Corvallis proceedings, which I mentioned, the 1970 proceeding, 2-volume proceedings, Symposia of Pure Mathematics that were published for the Corvallis conference in 1977. So we can write, here's the fact, this is a theorem proof, that's about 8 pages, an 8-page article. We can write irreducible representation pi as a tensor product. Okay, so those are based as a restricted direct product of rings, restricted a ring that is actually a restricted direct product of fields obtained by all of the completions of the rational numbers. And when we're using that notation to include the reals as well as the p-adic numbers, I guess we often write the index as v for evaluation, and so pi v. And okay, and so here's the thing that is particularly relevant, where each pi v, well, this is not the main issue, but it's what of course you would want in this, where each pi is an irreducible representation, and we could say unitary
although the general definition includes certain non-unitary ones, but is an irreducible unitary representation of GQV. And so, but here is what is really relevant, such that all but finitely many V's, for all but finitely many V's, or and these set that I'm throwing out, including the reals, that's in the finitely many bit, but such that for almost all pi V, but for almost all P, let's say, so I'm including almost all means just I'm restricting from the purposes of this statement to the primes. Almost all, for almost all the pi P, the irreducible representation of G, L, and QP is unramified. That's the theorem that was proved by Dan Flath. It was not stated. It was something that Langlands simply assumed. He didn't. He pointed it out that it's no doubt true and wouldn't be too hard to prove. In his 1969 article, 1977, it was agreed that this and various other things that were just taken for granted in Langlands should be written out formally, and they were. And so this was done by Dan Flath. His article is Decomposition. I'm missing something. This thing, I got to tell you what that is. But in any case, decomposition of representations into tensor products. That's just a little exercise in ring theory, which I wouldn't want to have to reproduce on the spot, but this is in the Corvallis proceedings, which I've mentioned before. It's part 1. Didn't write down the page numbers, but you'll find it easily enough. Okay, so but the point is that what makes automorphic representations, despite appearances, so very concrete. They are governed by very concrete, explicit data. And so that's what does that is the notion of unramified. What is unramified? What does it mean? Whatever it is, almost all of the pi p's in an automorphic representation, or really a generally irreducible representation, are going to be unramified. So, so suppose that that pi p is an irreducible representation. Unramified applies to irreducible representation. So suppose that's an irreducible representation of GQP, GLNQP. We've talked about this informally. If you have a representation of this locally compact group, you could restrict it to the maximal compact subgroup. And in the p-adic case, that maximal compact subgroup, it's not an orthogonal group the way it is for general linear real group. It's a group of integral points. So suppose this is an irreducible representation of this, then we can restrict it okay, to the subgroup. So it's open. That's also what's qualitatively different for p-adic groups. The maximal compact subgroup is not a closed subgroup like a submanifold. It's actually an open subgroup in the topology, in the p-adic topology. And the open compact subgroup KP which is GLN ZP. So the open compact subgroup KP of GQP, GLN QP. Okay. Well, what happens if you do that? That's a smaller it's a smaller group. So if you start off with an irreducible representation of the big group, you can't expect the restriction to the smaller group to be irreducible, but it's a compact group. And you no doubt know the theory of representations of compact groups. Any unitary representation of a compact group is a unique direct sum of irreducible representations of that compact group, each of which is finite dimensional. Well, I mean, this is an infinite dimensional representation, so we'd be talking about an infinite direct sum of irreducible representations of this maximal compact subgroup. So I'll say, so as a representation of KP, it's no longer irreducible. Now, what unramified means, and I'm going to say, I'll enlarge on it a little bit. What unramified means is if the irreducible representation upon restriction to KP, okay, and it's got a whole bunch of representations of KP in its decomposition. Representations, by the way, of groups GL and ZP are complicated objects. They're very interesting, but they're complex objects. But we ask to be unramified. We ask that its restriction to KP contain the trivial one-dimensional representation. That's what it means to be unramified. So, in fact, in order to present that the way we would like to see it, the restriction of pi p to kp that we're talking about here, well, I said it, it's a direct size of irreducible representations of KP, and I guess this is a further property that it has, each of which occurs with finite multiplicity. In other words, you wouldn't be able to have infinitely many copies of the one representation in this decomposition. Okay, but what's really relevant from our point of view is if you take pi p to be an irreducible representation of the big group, the trivial one-dimensional representation of K, which you get upon restriction, occurs at most once. It can occur with multiplicity 0 or 1 and nothing else. So moreover, the trivial one-dimensional representation of KP occurs with multiplicity 1 or 0. And so then now we can have our definition. Pi p is unramified if it contains the trivial one-dimensional representation of KP. That turns out actually to be a greatly simplifying condition upon an irreducible representation of the bigger group, as we will see in a moment. So it's unramified means it's multiplicity 1. Okay, so
that's about multiple equals G1 or 0 specific to GLN, or does it work for?
Works in general. You have to be a little bit careful. You have to talk about an unramified group. It's just a buzzword. It works for any split group. It also, you have to be careful with, I don't want to say too much just to confuse the matter, but there's something called a split group, something called a quasi-split group, and something called a general group. And this works for split groups, it works for quasi-split groups, this definition, but there's a hook in it, and that is, unlike the case of real groups, the maximal compact subgroups of a p-adic group are not all conjugate. The maximal compact subgroups of a real Lie group are all conjugate to each other, so it doesn't matter which one you take. For p-adic group, that's not the case. So that's just, I mean, it's a technical point, an interesting. All these technical points are things where the data is very interesting, but it's so you have to be careful about that. But yes, this works in general. So I'm restricting myself to GLN because it is in some ways very representative of what happens in general. Okay, so here's a little appendix. So unramified representations contain very, yes, Wally.
This fact in general by that fact, this also is for any G, not just for GLN.
That's right. That's what yes. Yeah. It's for any G with the technical property that I didn't really define for any unramified group G.
And do you start with a unitary irreducible representation or just any irreducible representation?
You can start with any irreducible representation.
I see.
You have to make it continuous in a certain sense, but.
I see. And then this one, when you this fact you have in the theory of Lie groups, so representations of compact Lie groups, you would get this by standard results, but like this is not a. These are not, they don't have a real topology, right? They have a p-adic topology, but with the same fact holds and it's the same.
That's right. What I'm saying here actually for p-adic groups actually goes over, and many of you may be familiar with this, it goes over for real Lie groups too, about the restriction, the notion of being unramified we reserve for these p-adic groups. But the classification, for example, of these representations of real Lie groups, these representations actually does carry over to real groups. But what's really relevant here for the data that comes in, that lies in an automorphic representation is what these are, the almost everywhere components, and particularly what are the parameters in them which classify the unramified representations. Okay, so for that we have to just state classification, and this is very interesting stuff, but it's not as deep as the Langlands program. It's well known, has been well known for a long time. So the classification of unramified representations of GQ. All right, so they basically come from induced representations, and so you introduce a group which you always are always a big part of this story, the maximal solvable subgroup, or what's better known as the Borel subgroup. So the standard Borel subgroup consisting simply of the group of upper triangular matrices, invertible matrices in GLN. So we would ask that BII lie in QP star. So this is known as the Borel subgroup. Any split group or any quasi-split group has a Borel subgroup, which is defined over the same field, and they are all conjugate. So this group of upper triangles is this is called the standard one for GLN, because you can actually choose a canonical one among that conjugacy class, the group of upper triangular matrices in GLN. That's the Borel subgroup of GQP. Okay, so how do you construct representations of that? This is a natural and straightforward construction that many of you will be familiar with. Let me choose an n-tuple of complex numbers, un and cn. And then to describe the representation that you associate with this n-tuple, this is u1 up to un. So let me define one. I will use it to define a character, a one-dimensional representation of the Borel subgroup. Let me write chi-u of b equal to the diagonal elements, basically raised to these powers u, these complex powers u. There's a slight hitch in it. You actually take u1 plus n minus 1 over 2, b22. This is, of course, the p-adic absolute value of these p-adic numbers. And you take u2 to the n minus 3 over 2, and so on, down to bnn to the un minus n minus 1 over 2. This would be for any b in BQP. That the reason these rather ugly looking real indices come in is a phenomena that it has to be built into an induced representation when the subgroup you're inducing from is not unimodular. GLN is unimodular. That means its left Haar measure is the same as its right Haar measure, but that is not the case for this solvable subgroup. And you got to be a little careful when you're the numbers don't work out right if you're inducing from a non-unimodular subgroup. And it turns out what you have to do is put those things in. The reason why you put them in is you want to know that if you have a unitary representation of the subgroup, and when you induce it up to G, it would also be a unitary representation. And that is not the case if you don't put these things in. So we'll. Yes.
Wait, is that what's that letter? Chi? Is this a character?
Yeah, this is supposed to be a chi. This is a character. So this is a character. So that's a homomorphism from BQP to C star, multiplicative groups.
So like you start, so you.
Pardon me?
The UI are complex parameters.
They're just they're the things that you're really interested in. These little things are a nuisance, a nuisance because you're dealing with a subgroup that's not unimodular. If you don't put them in, then if the UIs are purely imaginary, and so that this character is purely imaginary, then the induced representation is not going to be pure unitary. It's just there's no need to go into this. It's if you fool around with GL2, you'll see what the problem is, and why you have to put those in. It's they're basically those n minus n1 up to if the u's were all 0, then you'd have a real character, and that character is what's known as the modular function of this group BQP. Modular function is the difference between the left Haar measure and the right Haar measure. So you got to it's actually the square root of the modular function. And you got to put that in so things work out to be unitary. All right. So anyway, that there's this, given this data, you've got a very natural one-dimensional representation. So now I have to define the space. I have to define the induced representation. So there's a representation non-unitary, the way we've got it set up there. I have to define the space of the induced representation. So let me write VP or VPU to be the set of functions phi from GQP phi such that it behaves in a natural way under left translation by the subgroup. B of Bx is equal to phi is equal to transforms under left translation by B according to this character. Chi U of B, P of X. Okay, so I would ask that, take this space, it's not functions on G mod B, but rather functions on G that transform in a certain way, namely by this character that's governed by the n tuple of complex numbers. And then what we can do is we have a way then to write a representation of GQP on this space by right translation. And so I'm going to write pi, I will write pi tilde actually, but PU of Y is the operator that sends a phi in this space to the new function in that space, whose value at X, we've written this sort of thing down a number of times, is just right translation. So phi in VPU and Y in GQP. And F is a function. Good. Thank you. Thank you. That was, yeah. Yeah, thanks. Okay. Then you check that I tilde PU, this is by definition, this is the definition of an induced representation. As an induced representation. So you check just a little bit, you have to check it a little bit to see that it actually is a representation. It's multiplicative in Y, and it's an induced representation, which is infinite dimensional, at least if n is not equal to 1. There's nothing, the Borel subgroup is 1 in the case of GL1, so there's nothing to do there. So it's an induced representation of GQP, infinite dimensional on this vector space VP. And a couple of facts. So we're not proving these things, but they're standard things. This is what I mentioned before. Pi PU is unitary if chi U is unitary, i.e. U1 up to UN lies in R. The U's are complex numbers, but when you raise something to a complex power, it'll be unitary if it's an imaginary real number. So that's condition for it to be unitary. The thing that's really relevant for this, it's usually irreducible. So it's unitary, usually irreducible. But you have to account for the case where it is not irreducible. And then turns out it has finitely many irreducible constituents, but there's exactly one of those constituents that is unramified. So usually irreducible and always has a unique constituent I'm using the word constituent here because this is perhaps something you get from modules of modules of rings. If it's not a unitary representation, if these U's are not unitary, then the decomposition of pi u, pi pu into irreducible representations, there's only finitely many irreducible components, but it's not a direct sum. It's a direct sum if it's unitary, but it's not necessarily a direct sum. So you have to talk about quotients and subrepresentations, just like you talk about Jordan-Holder factors for a module over a ring. But nonetheless, there's always a unique irreducible constituent that is unramified. So the whole thing's unramified if it's irreducible, but there's always a unique one that is unramified in general.
Sorry, what is the word induced representation mean?
Oh, that's by definition then def. That's a definition of an induced representation in this context. I didn't give the general definition, but general definition is the same way. You have a subgroup and a representation of the subgroup. Then you take the set of all functions on the big group, which behave under left translation according to the representation of the subgroup. And then the representation of the big group is by right translation of the whole thing. That's the definition of an induced representation. Modulo this little technicality that we got to put in these characters to account for the fact that the smaller group might not be unimodular. Any other questions? Yes. Pardon me? It turns out to be irreducible, and this is special to GLN, whenever the U's are purely imaginary. So whenever it's unitary, it's irreducible for GLN. But that's not something one can accept when you're dealing with other groups. And then for GLN, it's basically where all of the, where one of the constituents, the U's, happens to be integral. Yes. So if they're all integrable, you get more constituents. So if it's purely imaginary, it could be any values, but then there's also the real values at the integers. Those are the ones that tend to be. I'm not saying that they're always reducible, but they're the ones that are typically reducible. It's an interesting problem. People work on that. So I think it's well known for GLN what happens, but they work on that for other groups, just people that study p-adic groups. When is the induced representation? Because the induced representation, this is the sort of simplest way that you can get representations of p-adic groups, but by induction. But then it's important to know when they're irreducible, or if they're not irreducible, what the irreducible constituents could be. And by the way, so I'm saying that for GLN, they are irreducible if they're unitary, The induced representation is irreducible if it's unitary. If it's not unitary, that means the U's could be real. You know, I forget what remark I was going to make, so forget about that. It'll occur to me in a minute. Okay, so always a unique. So so that is unramified. It always has a unique irreducible constituent, which I'm going to write. I put a tilde on the one that could be reducible. And so then I'll write pi p u without the tilde on it to be the irreducible constituent. So what do we get? For every u, n tuple of numbers u, we get an unramified representation of GQP. Using this fact here, you take the induced representation, and then there's always a constituent that's irreducible. So it's always there's always a unique irreducible constituent that's unramified, and moreover, any unramified representation of GQP is of this form. So this is all for GLN, but it's slightly more complex for other groups, but this basic idea is what carries over. Any unramified representation of GQP is of this form. So you could then, if you were to think about this, if you weren't familiar with it and you were to take it away and think about it for an hour or two, there's one remaining question you'd want to know the answer to. You get all you get all unramified representations of GQP by choosing numbers, complex numbers, U1 up to UN. Is there any overlap for different numbers? In other words, is the map which sends unramified representations of p-adic groups to n tuples of numbers, is it a bijection? And it's not quite. So finally, what if you have two different u's? Finally, if u prime equals u1 prime, un prime, there's another n tuple of complex numbers, then the corresponding induced representation, the corresponding unramified representations that we obtain from these by induction are equivalent. Pi p u prime is equivalent to pi p u if and only if u1 prime, un prime, not quite the same, but one is a permutation of the other. So u sigma 1, u sigma n. So actually there's two things. One is they could be equivalent if when they are equivalent, in fact, if you permute the entries. And the other thing is I've got a congruence condition, which is mod 2 pi I to the log p to the n. All right, that's an n tuple of complex numbers. And if the n tuples are congruent, even if they're if the n tuples are congruent, modulo this n tuple, then you're going to also get the same representation. And this would be, the sigma is just for some sigma in the symmetric group. So what we do, given this fact, we can package this data that characterizes unramified representations. We can characterize it nicely. Let's write C pi p u to be. So I'm going to define a complex diagonal matrix. I'm going to attach a complex diagonal matrix to this n-tuple U, which carries this information. I would take P to the minus U11, excuse me, P to the minus U1, all the way down to P to the minus UN. I take P and I raise them to the UNth power. And then that's why I have this congruence condition. The data I want to keep in mind, the data I want to single out that characterizes these representations. I want to write it in this form. This is a complex matrix. And I want to write it, I want to take P to these power of these things. That's why you have this. The power of U is the reason for this. And what about the possibility of permuting these things? Well, all we do is we take the diagonal matrix and regard it as something a little, not quite the diagonal matrix, but rather the conjugacy class in GLNC of that diagonal matrix. So regarded as a, I'll write, say, semi-simple, meaning it doesn't have any Jordan blocks, a semi-simple conjugacy class in the complex group. So the complex Lie group and so this is sort of, we see something creeping in here that's at the foundation of the Langlands program. You got the group G, and now you got another group, which people write as G hat. In the case of GLN, it's the same group that you start with, except you consider its complex points. So G hat equals GL and C. And this thing here, Langlands didn't introduce this notation. It came later. It's due to Kottwitz. But Langlands, this is now known as the Langlands dual group. Of GLN regarded as a rational group over Q. So it happens to be the same group in this case. It's a complex group. And the purpose of these complex groups are to carry the parameters that characterize the unramified representations. So this is concrete. It's really concrete, you know, the diagonal, just a conjugacy class, a semi-simple conjugacy class given by diagonal matrix in GLNC. And so if you have an automorphic, I'll emphasize this again next time, but if you have an automorphic representation of GLN, what does it hand you? It looks very abstract. It looks, how is this going to give you concrete things about number theory, you might ask? It looks very abstract, but right at its heart is something very concrete. For almost all prime numbers, a conjugacy class in GLNC, or if you prefer, a diagonal, complex diagonal matrix determined up to permutation of the entries. Question? Okay. Okay, we're back to Fields Institute on Friday.